Hello students, yesterday we have completed some of the examples on determinants by using the properties. Now we are discussing second type of examples. In this type of example, we try the proof of the result by adding all the rows or all the columns. Now that type of another example we consider here, that is by using properties of determinants, prove that x plus y plus 2z x y second row z y plus z plus 2x y third row z x plus x plus 2y it is equal to 2 times of x plus y plus z whole cube. This we can prove by using LHS. Now I consider LHS. It is x plus y plus 2z. It is x y second row z y plus z plus 2x. It is y, it is z x z plus x plus 2y. Now before operating rows or columns, we check by which we are getting the common term. If you add all the columns, here x plus x is 2x, here y 2y, and here 2z. Totally we get 2x plus 2y plus 2z. Here also z plus z 2z, y plus y 2y, it is 2x. Here also z plus z 2z, x plus x 2x plus 2y. Means everywhere you are getting the common term, that is 2x plus 2y plus 2z. That we take first. By taking row transformation, we are not getting the common term because by adding r1 plus r2 plus r3, we are getting all three different. For that we don't take row transformation. For that we take only column transformation, taking C1 as C1 plus C2 plus C3. Then we get it is equal to, it is C1, it is C2, it is C3. Now we are adding all the columns with first column, that is x plus y plus 2z plus x plus y. Second element z plus y plus z plus 2x plus y, and adding all the three, z plus x plus z plus x plus 2y. It is nothing but C1 plus C2 plus C3. Remaining two columns as it is, x y plus z plus 2x x, and third column it is y z plus x plus 2y. It is as it is. Now we are changing only the first column. Now after simplifying this, you add x with x, 2x, y with y, 2y, and 2z. Now we can get it is 2x plus 2y plus 2z. Similarly, here z plus z 2z, y plus y 2y, it is 2x. Here also we get 2x plus 2y plus 2z. In third element, here also z plus z 2z, x plus x 2x, it is 2y. Here also we get 2x plus 2y plus 2z. Now second column as it is, x y plus z plus 2x x. Third column y z plus x plus 2y as it is. Now we observe that in the first column, that is C1, we are observing that every element is same, that is it is possible to take outside from the first column by using third property. For that we write taking 2x plus 2y plus 2z common from C1, that is first column. Then we get 2x plus 2y plus 2z outside. Then we get first column is 1 1 1 because we taken outside. Next remaining column as it is, x y plus z plus 2x x. Third column as it is, y z plus x plus 2y. Now we try for 2 zeros here. It is possible if you take R2 with R1 and R3 with R1, that is subtraction. It is R1, it is R2, it is R3. If we take R2 minus R1, we get 1 minus 1, 1 0. R3 minus R1, we get 1 minus 1, 1 0. For that, we take that transformation, taking R2 as R2 minus R1 and R3 as R3 minus R1. Now it is equal to, here 2 is common, 2 into x plus y plus z I will write, it is outside. Now we transform this, we are changing only R2 and R3, R1 as it is, 1 x y as it is. Now it is 1 minus 1, it is R2 minus R1. Here y plus z plus 2x minus x, it is R2 minus R1. It is y minus y. Similarly here R3 minus R1 is 1 minus 1, it is x minus x. Here z plus x minus plus 2y minus y. This stuff we get after subtraction. Now simplify this. It is equal to 2 times of x plus y plus z into determinant. It is 1xy first row as it is. Second row we get 1 minus 1 is 0. It is y plus z plus 2x minus x, means 2x minus x is x. We get y plus z plus x, y plus z plus x. Here y minus y is 0. Next we go for third row. It is 1 minus 1 is 0. It is x minus x 0. Now z plus x plus 2y minus y. 2y minus y is y. We get z plus x plus y. Z plus x plus y. Now it is equal to, now here we observe that here below the principal diagonal elements, every element is equal to 0. Therefore it is upper triangular matrix. If it is triangular matrix, the determinant value is equal to product of diagonals. Therefore write it as 2 times of x plus y plus z into product of diagonal elements are 1 into y plus z plus x is nothing but x plus y plus z into z plus x plus y is also x plus y plus z. Now we get 2 times of, here x plus y plus z 1 time, 2 time, 3 time, total it is x plus y plus z whole cube. This is equal to RHS. Like that we prove the result by using the transformation, that is C1 equal to C1 plus C2 plus C3. Then we get the common terms as 2x plus 2y plus 2z. After taking common, we get 1 1 1. By subtracting R2 minus R1 and R3 minus R1, we are getting the required answer for the right hand side. Like that we solve the example. Write this. Next we go for another example. Prove that by using properties of determinants, prove that 1x x square 1x x square 1, it is equal to 1 minus x cube whole square. This we can prove by using LHS. First we take LHS. LHS is 1x x square 1x x square 1. It is LHS. Now using this we can prove the right hand side by using the properties. This can be done either row wise or also column wise transformation. Now if you take column wise transformation, if you add all the 3 columns, it is 1 plus x square, it is x square plus 1 plus x, it is x plus x square plus 1. Everywhere we get same term, that is 1 plus x square by adding the columns. Otherwise we can try by row wise transformation also. Now it is C1, it is C2, it is C3. Now I write taking C1 as C1 plus C2 plus C3. Adding all the columns with first column, we get it is 1 plus x square. It is also 1 plus x square. It is also 1 plus x square. Now x plus x square plus 1 is nothing but 1 plus x square only. Now remaining two columns as it is x1 x square x1. Remaining two columns as it is. Now we take common from first column because it is same for first column. Therefore we write taking 1 plus x square common from C1, that is first column, we get it is 1 plus x square outside. Now the first column changes to 1 1 1 because we taken outside 1 plus x square term. The second column is x1 x square as it is, and third column x square x1. It is also as it is. Now after getting 1 1 1 terms, we try for zeros. Here we make two zeros here by taking this minus this and this minus this. That is, it is R1, it is R2, it is R3. Now if we take R1 minus R2, we get 1 0, and R1 minus R3 minus R1 also 1 0. Now we change R2 and R3 like that, R2 minus R1 and R3 minus R1. Because of we are getting two zeros, for that I write taking R2 as R2 minus R1 and R3 as R3 minus R1. Now R1 kept constant, it is 1 plus x square as it is. First row 1x square as it is, because we are changing only second and third row. R2 minus R1, it is 1 minus 1. Here R2 minus R1 is 1 minus x. R2 minus R1 is x minus x square. Similarly, R3 minus R1, 1 minus 1 x square minus x. Here 1 minus x square. Like this we get. Now we simplify this. 1 plus x square as it is. Now 1x x square, first row as it is. Here 1 minus 1 is 0. It is 1 minus x. Now here we observe that x is common. We get 1 minus x. Now 1 minus 1 is 0. Here we get common x. If you take x common, you are getting x square minus 1. But for getting 1 minus x, we take minus x common. We are getting x minus. If you take minus x common again, 1 minus x. Minus into 1 is minus x. Minus into minus x is plus x square. Again we are writing above steps. Here it is 1 minus x square is there. It is written as 1 minus x into 1 plus x. Because 1 minus x square can be written as 1 square minus x square. A square minus b square is a minus b into a plus b. Now it is 1 minus x into 1 plus x. Now here we observe that in the second column 1 minus x is common, and third column is also 1 minus x is common. Now we take common from second column and first column. It is C1, it is C2, it is C3. Now write taking 1 minus x common from C2 and C3 respectively. Then we get here previous is 1 plus x square as it is. Here 1 minus x, again 1 minus x, 2 times we are taking, it is 1 minus x whole square. Because from here we taken 1 minus x, from here also we can taken, that is 1 minus x, it is from R2, it is from R3. From R2 we have taken 1 minus x common, and from R3 also we have taken 1 minus x common, that is we are getting 1 minus x into 1 minus x, that is 1 minus x whole square. Now first column we are changing, second row and third row, it is 1x x square as it is first row. After taking common in the second row 1 minus x, we are getting 0 1 x 0 1 x. Here taking common in the third row 1 minus x, we are getting, it is 0 minus x, it is 1 plus x. Now simplifying this, 1 plus x square into 1 minus x whole square. Now we expand this determinant, first 1 into determinant, next minus x into determinant plus x square into second determinant. Here plus minus plus. Now first we write 1 and we write the determinant of second order, next we write plus x square minus x into second determinant plus x square into third determinant. Now deleting this column and this row, we get 1x minus x 1 plus x. It is written here. Here minus x outside, by deleting this column and this row we get 0x 0 1 plus x. Similarly in third, deleting this column and this row we get 0 1 0 minus x. Now it is equal to 1 plus x square as it is, 1 minus x whole square into, expand this determinant, it is 1 plus x minus of this, that is minus of minus is plus x square. This we get, remaining are 0 minus 0, it is also 0 minus 0, we get minus 0 plus 0. Now it is equal to 1 plus x square, it is also 1 plus x square, we are getting 1 plus x square whole square into 1 minus x whole square as it is. Now I write it as 1 plus x square into 1 minus x whole bracket square. Instead of writing separate square, I will write it as whole bracket square, because this formula, it is a square b square is formula equal to ab or a raised to n b raised to n equal to ab raised to n. Using this synthesis formula, we written like this. Now it is 1 minus x into 1 plus x square formula. It is nothing but 1 minus x cube and whole square as it is, because the standard formula is, it is 1 minus x into 1 plus x square, it is always equal to 1 minus x cube, that is 1 cube minus x cube, that is a cube minus b cube equal to a minus b into a square plus ab plus b square. Using that formula, we are writing this step, that is 1 minus x cube whole square. It is nothing but RHS. Like that we prove the result by using this formula at last step, that is standard formula is a minus b into a square plus AB plus B square equal to A cube minus B cube. This is the applied formula for last step. By using that we get the right hand side value, that is 1 minus x cube whole square. Take this solution. Next we go for another example. By using properties of determinants, prove that a square plus 1 ab ac, first row, second row ab b square plus 1 bc, third row ca cb c square plus 1, it is equal to 1 plus a square plus b square plus c square. This we can prove by using the properties of determinants. Now first we take LHS of this. LHS equal to a square plus 1 ab ac ab b square plus 1 bc ca cb c square plus 1. Now we observe that by taking r1 plus r2 plus r3 or c1 plus c2 plus c3, we don't get any common term here, because adding all the rows or all the columns we get all are different. It is not possible directly now. Otherwise, is it possible of making any zeros here by subtracting any row with any column? It is also not possible, because if you tried for any r2 minus r1, c2 minus c1, c1 minus c2 like that, we are not getting any zeros here. For that, first we convert the given example into standard form, then we go for the transformation. For that, we go for some of the trick for this one. I will multiply and divide by first row by element A, and similarly the second element, that is B, by second row, it is multiplied and divided by this second row, and for the third row I will take the element C, that is multiplied and divided, that is A square plus 1 into A divided by A, AB into A divided by A, AC into A divided by A. This first row is multiplied and divided by A. Similarly, AB, you multiply this by B and divide by B. Now B square plus 1 multiplying and dividing by B. BC multiply B and divide by B. Similarly, third row by element C. CA into C by C, CB multiply by C divided by C, and C square plus 1 multiply by C divided by C. Again these A and A get cancelled, there is no change in the previous value, it remains constant. Similarly for R2 and R3, there is no change in the previous result, same way multiplied and same way divided. What we did here, because multiplying and dividing R1, R2 and R3 by A, B and C respectively. Multiplying and dividing by A for R1, multiplying and dividing by B for R2, and multiplying and dividing by C for R3. Now we take the common term in the first row, that is 1 by A, it is common for R1, and 1 by B is common for R2, and 1 by C is common for R3. First I will take common terms 1 by A, 1 by B, 1 by C from R1, R2 and R3 respectively. That is taking 1 by A, 1 by B and 1 by C common from R1, R2 and R3 respectively. Now we get, if you take 1 by A from R1, what you get here? It is R1, it is R2, it is R3. You take 1 by A from here 1 by A will take outside from R1, it is 1 by A, 1 by B, 1 by C, it is 1 by A from R1. 1 by A if you take outside, what left here? Here A square plus 1 into A. Here if you take 1 by a, what you get here? Here a into ab. A into ab is a square b. Here 1 by a is taken outside. What left here? A into ac. A into ac is a square c. It is first row. Similarly in the second row we taken 1 by b outside. That is 1 by b, 1 by b and 1 by b outside we get ab into b first here. ab into b is ab square. Here 1 by b is taken outside. We get b square plus 1 into b. Here 1 by b outside. It is bc into b. That is b square c. It is for second row. Similarly third row changes to 1 by c we taken outside already here. Now we get ca into c, that is c square a. Now cb into c, 1 by c is outside already. cb into c is c square b. Now here 1 by c is outside, we get c square plus 1 into c. c square plus 1 into c. These terms we are getting after taking 1 by a from R1, 1 by b from R2 and 1 by c from R3. Now we observe once again that a is common in the first column and b is common in the second column and c is common in the third column. By using third property we can take outside these three terms. Here outside term 1 by abc as it is. Now we write taking a, b and c common from c1, c2 and c3 respectively. Then we get it is 1 by abc outside as it is. Now once again we are taking abc common from c1, c2 and c3. Then we get another a, b and c terms. Then the determinant changes to it is a square plus 1. If you take a outside from first column, we get a square plus 1 b square c square. Similarly, if you take b from second column, we get a square. It is b square plus 1. It is c square. And third column is a square, b square, c square plus 1. Because here c is taken outside. Now these two get cancelled. Now we get the determinant as a square plus 1, a square, b square plus 1, b square, plus 1, b square, c square, c square plus 1. That means we are changing the given determinant into another determinant by transforming some row and column transformation. Now we observe that for getting the right hand side, you observe that here answer is 1 plus a square plus b square plus c square. Now how can you get this answer? Just by observing the determinant, we see that if we add all the three rows, we get the direct answer for that. That is here R1, it is R2, it is R3. If we add all the three rows, we are getting the term a square plus b square plus c square plus 1. It is also a square plus b square plus c square plus 1. It is also a square plus b square plus c square plus 1. Means we are getting the same terms. Then we get it is a square plus 1 plus b square plus c square, a square plus b square plus 1 plus c square. It is a square plus b square plus c square plus 1. Remaining rows as it is b square plus 1, b square, c square, c square plus 1. Because what we done here, taking transformation R1 as R1 plus R2 plus R3. By taking this transformation we get this result. Now Once again you observe that 1 plus a square plus b square plus c square is common in the first row. We take common, taking 1 plus a square plus b square plus c square common from R1, means from first row we get it is equal to 1 plus a square plus b square plus c square, and determinant changes to here 1 1 1 first row, and second row is b square plus 1 b square, and third row is c square plus 1. Now we get 1 1 1 in the first row. For that we try for 2 zeros. It is possible if you take c2 minus c1 and c3 minus c1, we get 2 zeros. Here it is c1, it is c2, it is c3. Column wise we write taking c2 as c2 minus c1 and c3 as c3 minus c1. Then we get outside as it is 1 plus a square plus b square plus c square as it is. Now it is 1 b square c square. It is as it is first column. Now you take c2 minus c1 means 1 minus 1, it is 0. b square plus 1 minus b square, it is 1. c square minus c square is 0. Similarly c3 minus c1, 1 minus 1 is 0. b square minus b square is 0. c square plus 1 minus c square is 1. This stuff we get. Now we observe that it is a determinant of triangular matrix, because here above the principal diagonal elements each element is equal to 0. Therefore it is lower triangular matrix determinant. Therefore the result is equal to product of the diagonal elements. Now we write it as 1 plus a square plus b square plus c square into product of diagonal elements is 1 into 1 into 1. So it is 1 plus a square plus b square plus c square into 1. So answer is 1 plus a square plus b square plus c square. It is equal to RHS. This term we get by using simplification of this one, that is equal to RHS. Like that we prove the result by using some of the properties of the determinants. Write this example. Next we go for another example. Prove that by using properties of determinants we can prove that here b plus c a first row, b c plus a b, it is second row, c a plus b, it is third row. It is equal to 4 times of abc, that is right hand side. Now we take LHS for this. LHS is b plus c a, second row is b c plus a b, third row is c a plus b. Now by observing the determinant we see that here we get the sum zeros by subtraction. That is, if you take a minus a you get 1 0, but here the term is c plus a minus b. Instead of 2 terms writing 3 terms here by subtraction. So it is lengthy to evaluate. For that we don't go for directly subtraction here. We get another method for making 0 here. Another method is that here you observe that b plus c is present in the first row. It is R2, it is R3. Now b plus c present here, here b it is c. If we add b with c we get b plus c. Then if you subtract this b plus c with this b plus c, we are getting the answer 0. This transformation we are taking for making 0 for this example. Now for that we can take the transformation like that, taking R1 as R1 minus R2 minus R3. What is done here? because R1 is B plus C, minus R2 means minus B, minus R3 means minus C, B plus C minus B minus C. Is it 0 answer? For that reason we are taking this transformation. So we get this B plus C minus B minus C. It is R1 minus R2 minus R3. Here the same. A, C plus A, C is there. We get A minus C minus A minus C. It is R1 minus R2 minus R3. Here also same. A minus B minus A minus B. This is nothing but R1 minus R2 minus R3. The reason for that is here we get the element 0 and we are not getting more than 2 or 3 terms after the subtraction. For that reason we are taking this one. Remaining rows as it is B, C plus A, B as it is. Third row C, A plus B also as it is. Now simplifying this we get here plus B minus B plus C minus C get cancelled. We get it is equal to 0 and next element here plus A minus A cancel, minus C is minus 2C we are getting. Here again minus A plus A get cancelled, minus B is minus 2B. It is first row. And second and third row as it is B, C plus A, B, and third row C, A plus B. It is also as it is. Now we observe that in the first row minus 2 is common here. We take outside from R1. Taking minus 2 common from R1. It is first row, it is second row, it is third row. Now if we take minus 2 from R1 we get minus 2 is outside. It is 0 means 0 into minus 2 it is understood. Therefore minus 2 is common for R1. Now we get 0, it is C, it is B. Second row as it is B, C plus A, B. Third row as it is C, A plus B. This stuff we get. Now we try for 0. For that if you take this row transformation R1, R2, it is R3. Now if you take R2 minus R1 you are getting 1 0 and R3 minus R1 you get here 1 0. For that we take the transformation taking R2 as R2 minus R1 and R3 as R3 minus R1. Now we get minus 2 as it is 0, C, B as it is. We are changing only R2 and R3. It is B minus 0. B minus 0 is B. C plus A minus C. C plus A minus C is A. And B minus B is 0. Similarly, third row C minus 0 is C. C minus C is 0. A plus B minus B is A. This stuff we are getting. Now we go for expansion. It is plus minus plus. It is minus 2 into 0 into any determinant is 0 minus C and second determinant plus B into second determinant. Now 0 to number is 0. You don't write this determinant, directly go for this minus C as it is. Deleting this column and this row we get 0 B 0 C A. That we write here B0 C A. Now after that this element, for this element deleting this column and this row we get BAC0. BAC0. It is written like this. Now we simplify this. It is equal to minus 2 as it is into here 0 into number is 0 minus c as it is. Expand this determinant. It is diagonal elements minus product of non-diagonal elements. B into A, AB minus C into 0, 0. That is AB minus 0 plus B as it is. Expansion of this first diagonal B into 0 is 0 minus C into A is AC. It is 0 minus AC. Now it is completed. It is minus 2 into bracket 0 minus C into AB is minus ABC plus B into minus AC is again minus ABC. It is minus 2 as it is. Minus ABC minus ABC. What is this? Minus 2ABC it is. Now minus 2 into minus 2 is plus 4. It is ABC as it is. It is your right hand side answer, that is equal to 4ABC. Write these today's important examples for exam point. This example also appeared in your exam for 4 marks question. It is for 4 mark. Write an important question and write the solution.